So, multivariate functions. Typically until now, you have dealt with functions, at least that were explained to you, that were in one variable. For example, you have learned something like this, where you say, okay, f of x is equal to 3x squared plus 5x minus 2. And if we say f of 5, then you'll say 3 times 5 squared plus 5 times 5 minus 2 equals whatever. And we have one argument, which is what we call this, the argument of the function, and of course one independent variable. And you have done a lot of your math over the years based on this single variable concept, and that's wonderful. However, as we learned in grade 11, a position variable, if nothing else, is going to be in 3 dimensions. And so, at least in Cartesian form, it's going to be x, y, and z. And we can have motion on one or any or all of the axes. And so what we're doing here is to think about how we model that, how we can use our mathematical constructs to describe these things. And so we're talking now about a function of more than one variable. You have seen this before. This is not completely unknown. Consider the volume of a cylinder. So V sub c would equal pi r squared h. As you were taught in elementary school, one hopes. Well, what does the volume of this cylinder depend upon? It depends on the radius of the cylinder. It also depends on the height. And the radius and the height are independent of each other. One does not affect the other. So V sub c depends on r and h, and r and h do not affect each other. And when that is the case, we say r and h are linearly independent, or simply just independent to save us the words. And that's important when we do these things. So we could write the following then. We don't want to write, for example, so V sub c could not be V of r because we have this h. Nor could it be V of h because we have this r. So we have to write V sub c at r of h equals pi r squared h. And then given a radius and a diameter, we could say V sub c at 2 comma 1 is equal to pi 2 squared times 1, which in this case would be 4 pi, I suppose. And so the point here is this is a computation that almost all students have done when they were younger. And so you're dealing with a function of more than one variable, and no one's telling you are. Okay, you kind of found out by accident. And this is arguably true for differential equations too. And I don't think we should apologize for that, but we just need to make people aware that it isn't so new an idea that you haven't seen it before. Now, if we look at what can we do here? So in the case of f of x equals, say, as I said, 3x squared plus 5x minus 2, we have a mapping in the real numbers from a real number here to a real number here. So the argument of the function is a single real number, whatever it is. And when you're finished here, you get a real number out of it. Okay? This could still be a vector. It could be going left or right on a number line. So it could be negative or positive and have context. But it is nothing more than that. But we could also do something, we can do different things like this. We could have an equation like this one. F of xy equals, let's say, x squared y equals z. And we saw this with respect to the volume computation. So this is, the input here is R2, and it maps to a single real number. So in the case of the volume computation, we had a radius and a height argument, and we got out a single number for the volume. You could also look at it another way. We could have, say, a surface and say, okay, we're mapping all the temperatures. If we were smart enough to know what the equation would be, then you put in an x and a y, and wherever that point is, that's the temperature at that point, if you can come up with an equation that models that properly. And so this is another type of mapping that we use. We're going to do most of these for our calculations this year in R3. So let's look at what happens in these mappings in R3. What are the possible ones that can happen? So we can have a mapping of R to R3. All right. And this is generally known as a space curve. Okay, so we would have a line, a curve, and it doesn't have to be very smooth, so we could have a line like this in 3 space. Okay, but because we have an argument that's a real number, we can only slide along the line. Depending on what that x is, we'll only be able to move along. We can't go over here. We have to stay on whatever this geometry of this line is. And we'll come back to those because we're going to deal with that concept. And so this we call a space curve. That's one concept. We could have also R3 to R, which is basically the R3 extension to this idea where we have a position in 3 space, and at that point there's a temperature perhaps, or a density, or some other scalar quantity. And so these are known as scalar fields. And then we also can have a mapping of R3 to R3. So here, we'll use a location x, y, z, let's suppose. And at that point is a vector, a 3 vector. It could be, and the easiest one to think of would be velocity. So let's suppose that our classroom is a swimming pool and it's, 1.5 meters of water in it, and so it's all still. So anywhere you go in this, any point you choose, and depending on the resolution, of course, obviously there's going to be some small molecular level entities, but let's suppose it's pretty still. So we have basically zeros everywhere. Now we open the door. Now the water goes whoosh out the door. If you're near the door, okay, you're going to have some dramatic velocity vectors in x, y, and z as the water goes very quickly. But if you're over in the back corner of the room, the water will generally just be going down. So the point here is that the velocity in x, y, and z is very different in this room based on the location of that velocity. And this is what we call a vector field. Now it doesn't have to be a velocity, this can be any modelable concept, but this is a good example of it. Another location might be, say, in a gravity field, you say, okay, here's my location. What is the direction of the gravity force? And you might have more than one body, and so the gravity force is complicated. But as long as you have an expression that adequately shows it, you can do it. Now let's go back here for a second, at least in the general sense, and show how these functions are expressed. just so that you can, we're going to come back to them again anyway, but just to show you. So the first one is pretty much, we could have something like this, where we would have, and we'll use a different variable here, whatever, we'll just use f of x is equal to, so we could use an ordered pair here, or an ordered triple, pardon me. And so this could be x squared, this could be e to the x, this could be sine x, let's just suppose. So what we have here is f sub x of x, f sub y of x, and f sub z of x. And so this calculation then is organized in such a way that each of the coordinates is a function of a singular function of the argument of the function here. Okay? And so whatever you put in for x here, you're going to get, when you grind these out, you'll get a coordinate here that's based on these functions. And now you say to me, well, how do I know what they are? Well, that's the $50 question. I'm showing you the math just so you see the patterns. In the real world, if we wanted to find out something like that, we would have to say, well, okay, what is the shape of this curve? Okay. And then the x, y, and z variables would be such that as you get around it, you can model this shape. So when we generally do these problems at the beginning, we use canonical shapes. So we'll be using helixes and circles and things like that, so that the computations are not unreasonably difficult. The second example, if I haven't missed anything here, let's see. No, I think we're all right, at least so far. So my scalar field I've already kind of done, but I'll do it again just for sport. So we have x, y, z would equal something like maybe x squared e to the y sine z. But now, this is a scalar. This is R3, so 3 vector. And so, there we go. So that's the next version, which again is basically isomorphic to doing the computation. If you take the volume of a cube or a rectangle or something, a rectangular prism, the volume is length times width times height, right? Well, there's a function of 3 variables right there. So again, we've been doing this a lot longer than we want to admit. It's just that we didn't perceive it in this type of mathematical structure. The last one is a new one, as I already explained to you, but we'll just draw it up here. So if I have f at x, y, z, so let's put this down here. So once again, this is a space curve up here. And we're going to come back to space curves because we actually model them a little differently than this. This is kind of hard to appreciate. Okay, so I'm going to come back to these in a few minutes with a different type of approach, but it's still valid. It's not wrong, it's just we'll do it a little differently. And here we have our scalar field. And finally here, very similar to the space curve, but here we're going to have, if you will, a vector in each. I misspoke. Also, we're going to have a computation in each case. So this could be x squared y, x, y, z, and z e to the x. We don't have to include all 3 variables in each equation. We can, as we did in the center one, but it doesn't have to be. But the point here is that this vector, this 3 vector here, it's going to be a number here when you finish calculating, a number here, and a number there, x, y, and z, is going to be unique based on the position you choose. Now, again, what these equations are, that all depends on the physical system you're modeling. And that could take you a fair bit of time. We'll choose arbitrary functions, as we do in math class, simply to give you a chance to play around with this and make the calculations. Okay, now, the question that might be asked is, what do we do about the basics of calculus? So we will take derivatives, as you have many times in your single variable calculus. So let's just take a look here. So in single variable, so we have some f of x function, okay? The question here is, how does f of x vary as x varies? Now we have different techniques to figure this out, the product rule, the chain rule, this and that, the other rule, fair enough. But the concept is, how much and how does this change as a function of x varying? So now you say, well, gee, I have more than one, for the most part, I have more than one independent variable here. What happens? And that, of course, is a very good question. So first, what we're going to look at is the one where we don't have to change anything. In a space curve, so we just have df dx is simply equal to dfx dx, comma dfy dy, comma dfz dz. Okay? So just what you've always done. Nothing new, there's only one letter to worry about. The only difference here is we're going to take a derivative of each one independently, each coordinate separately, okay? So that isn't too bad. And notice, of course, that the derivative is also a vector, okay? That doesn't change. However, when we have more than one independent variable, we can generally express only part of the derivative at any time. So we can take the derivative, for example, of f with respect to x or y, etc. But it's pretty hard to take it with respect to all of them at the same time. And so such derivatives are denoted as partial derivatives. We use a slightly different symbol to indicate this. So d then becomes what we call die. Okay? So here we have the die operator, and by the presence of the die operator, you may not know what the variables are, but you know there's more than one. That automatically gives you pause. So, for example, we would write diaf dx for the derivative of a multivariable function Now, this, of course, is going to, you might say, my goodness, and understandably, the relief part is that the rules of doing these derivatives are very close to what you're used to with single variable calculus. And so everyone's blood pressure can go down a little bit. So in f at x, y, z, x, y, and z are independent. They do not affect each other. And so, when differentiating with respect to x, y, and z are constants, now, when I express this to my students the first time, you can almost hear the size of relief. Okay? So let's do an example or two here. So this makes a bit more sense, perhaps. So we'll do the first one here. Suppose we have v sub c at r of h equals pi r squared h. Okay? So now, and this is why I'm doing this, so a lot of students getting used to things have trouble changing from x and y to the variables of interest. In physics and real life stuff, we don't use x and y. X and y are just kind of generic variables so you can learn patterns. And we've got to get past that, folks. Okay? We've got to understand that one of the most common variables is time, okay? In this case, we have r and h. So if we do dv, dr, and something else here, just to show you this as well, notice that when we do this, we don't put the rh argument in there. We get it. If we see the function once, we already get what's involved. So having it every time is superfluous, and all it does is complicate and clutter up our mathematical expressions. And in physics, we really try to keep it as clean and as sleek as possible in these situations. So dv sub c dr, pardon, let's try that again, div sub c dr. What will happen here now is we're going to say, okay, well, pi is just a constant. We're differentiating with respect to r, and h is a constant. So what do we have here? We have 2r, okay? This is the standard product rule, or it's not the product rule, but whatever, you know what I mean. So 2 pi rh, okay? And if we did it implicitly, it would be also, we could also have div sub c equals 2 pi rh dr, okay? If you want to do it implicitly, you can do that as well. So as you can see, the calculus that you're dealing with is very, very much the same. If we do the other version, div sub c di h, we would have simply pi r squared. Okay, because the h is derivative of a constant like that is going to be 1, and so we just have pi r squared. So, and this makes some sense. If you think about it, how much would the volume of a cylinder change if we were messing around with the height? Well, it would be a function of the area of that cylinder, would it not? That makes perfect sense. So we need to be thinking a little bit about these things and be satisfied that we understand what's going on. Let's look at the other one for a minute too. We have here, how would the volume change if you're messing around with the radius? So now it's a little bit more different because we have this perimeter, okay, and the h. Okay, so it's a little bit different how much that's going to change. You have to think about that, and I'm going to let you think about it. It's important to just be mindful, especially when we deal with a case that's comparatively elementary, and you're learning how the calculus works. But start thinking about what it means as well, okay? So these are really important things. So I'm going to stop this lesson right now because I've done the introduction to multivariate functions and their basic derivatives so that I don't go too long on a given topic. Thank you for watching, and again, if you enjoy these lessons, please subscribe to this channel and tell your friends. Thank you.